So first step in doing this is you took your first line that you had here and you rewrote the cube root as a fractional exponent. Once you do that, then we can go ahead and find the derivative. Now, finding the derivative in this case requires chain rule because we got a function inside and we got a function outside.
That's what we do.
So when we do that, this is what we're looking at. But while this is technically the correct derivative, this is not the answer I want you to give. Your answer should be in the same format as your original question. The original question was given in simplified radical form. So our answer should also be in simplified radical form. So when you look at it, you'll notice that we got a power of negative 2/3 here. The negative exponent, remember, means that's going to flip into the bottom of a fraction. So we'd set up a fraction, and we know that we're going to have that 125 minus x cubed in the bottom of the fraction. Now that's to the power now of a positive 2/3. We're going to have to do something about that 2/3 in a minute, though. And then we distribute the rest of the stuff. So like the 1/3. Well, 1/3 means you got a 1 on top and a 3 on bottom. Not that you actually need that 1 on top, though, because also on the top is all of this stuff. Now, some of you might have looked at that and said, but it's negative. Yeah, but the exponent isn't negative. The number is negative. So it's still on the top. And so it'd look like that. But then once we've done that, we can go ahead and simplify it more. So we take that 125 minus x cubed to the power of 2/3, and we turn it into the cube root squared. And you'll notice that we got a 3 on top and a 3 on bottom, just number 3, multiplied in both top and bottom. So we can cancel those out as well. So then this is the final answer. This is what we should be looking at for y prime. Got a negative x squared over the cube root of 125 minus x cubed squared.
And we don't have to rationalize the
Little detail, actually a couple little details here. If you wrote the squared inside, so if you like wrote parentheses around this 125 minus x cubed and had that squared inside the cube root, yes, that means the same thing. And yeah, we could even go one step further if we wanted to in terms of rationalize the denominator, but I'm going to go ahead and let you stop here for the time being at least. On the second problem, our basic process is much the same. So you notice it's negative, but again, it's not the exponent that's negative, it's just a negative 1 being multiplied by the whole thing. So I go to find my derivative, which again is going to be chain rule. Here's my inner, here's my outer. And so when we do chain rule, the negative just stays out front of it. So that negative becomes that negative there in our derivative. I pull the exponent out front exactly as it was, and then I subtract 1 from the exponent to get my new exponent, hence the negative 1/2 exponent. The stuff inside stays the same, remember, with chain rule. We only change that when we take the derivative of the inner function. And the derivative of 49 minus x squared is the derivative of negative x squared, which is negative 2x. And again, from there, it's a matter of cleaning it up. Notice we have a negative exponent, so that's going to end up, that means that all of this stuff is going to end up in the bottom of our fraction. And then the 1/2 power tells us that it's going to be a square root that's in the bottom of the fraction. And once again, the 2's cancel out. In fact, the negative 2's cancel out, meaning that the answer is actually now positive because this negative and this negative multiplied to a positive. And of course, 1/2 times 2 is 1, so that's why they cancel out and we're gone. All right, now keep this worksheet handy. We're going to come back and reference it again tomorrow in some of our ongoing work, because this is actually a particular scenario of some other ones that we're going to be working with more. Yesterday, you remember you made all those crazy looking graphs?
No.
All of those were examples of implicit equations. Now, up until this point in your mathematical career, most equations that you've worked with have been explicit functions. And so they've looked like this sort of a thing. Basically, an explicit equation has it already solved for one of the variables, like y equals, or even x equals would be considered explicit. But an implicit equation is not solved for a single variable. So notice these two equations here actually describe the exact same situation. All that we had to do was take that 7x squared and move it to the other side, and it became an implicit equation. And so they often can be very closely related. In fact, sometimes the same equation can be written both explicitly and implicitly, but not all the time, as you're going to see. Some of them get really scary and ugly if you try to do that, which is why we need a way to deal with this. Because since we can write equations implicitly, we need to be able to write the derivatives implicitly, because there are some equations that you just can't do explicitly. So we're going to be going through this problem as our first example about how to find an implicit derivative. So go ahead and write down this problem. All right, so to find an implicit derivative, basically what you're doing is you're just going to go through and find the derivative of everything as you see it. It's just there's going to be one little twist in how you think about it, as you'll see. So, first thing I'm going to do is just do the derivative of 2x. Well, we know that. That one's nice and easy. That's just 2. So it's going to be 2 equals. And now we're going to do the derivative of y cubed. This is where things get interesting. Because you might think that it would just be 3y squared. But it's not. It's close to that, though, as you're going to see. Because y is just some function of x, right? I theoretically could take this equation and write it as y equals. And so that means that y is a function of x, or at least an equation that we can write in terms of x. It may or may not be an actual function. And so when we find the derivative of y cubed, we actually are using chain rule. Because we have the function y that is being cubed. And so if we're going to use chain rule here, that means derivative of the outer function, so we do the derivative of something cubed, which is 3y squared. But then we multiply that by the derivative of the inner function. Well, the inner function here is y. What's the derivative of y? Y prime. Because it's the derivative of y, not the derivative of x. And so, at this point, we have technically found the derivative implicitly. We now know the derivative. It's just that right now it's not written the way we're used to seeing it. So, we're now going to go ahead and take this equation and solve it for y prime. So, that just means dividing both sides by the 3y squared. So we're going to have 2 over 3y squared equals y prime. And so you'll notice that with an implicit derivative like this, you no longer necessarily end up with the derivative equation in terms of x. Your derivative equations will often, not always, but often include both x and y. This one's an example of where the x disappeared. So actually y prime equals something in terms of y. How could that work? Why would we do that? Well, think about what we've done with derivatives in the past. Like we'd find a derivative and then we'd find the slope of the tangent line by plugging x in, right? You could do the same thing here. Except if we had some point that this went through, let's say 0, 0, you'd actually be plugging the y-coordinate in to figure out what the slope is at that point. So same kind of an idea. Now, it's always useful to formalize this and give a few steps that we're going through on this. So these are the steps for implicit differentiation. These should go into your notes. And then we're going to do some more examples to see how this really ends up looking, because I know it's going to take some practice. All right, now, you got these down in your notes, I hope. If not, get it down now. A couple little notes here. So notice you find the derivative as the first step. It's just that when finding the derivative of a term involving y, you're having to use chain rule. Because remember, y is a function of x. So it really is a function within a function when you're finding the derivative of something with y in it. And then solve your equation for y prime, which is the last thing we did. In the last problem that we did, though, there wasn't really any simplifying we could do. But you'll find that oftentimes there can be some simplifying as we solve it. And there's actually some interesting things that come up with other simplifying, where you can like plug stuff in from the original equation. But we'll worry about that here as we go a little bit forward. We can save some of that more for tomorrow. For today, we're going to take a look just at a few more straightforward examples. At least I hope they'll be straightforward for us. Go ahead and write down this problem.
Why?
All right, so we're now going to go ahead and find our derivative. Notice, in order to find the derivative implicitly, we don't have to like solve it first for y. We don't have to worry about doing anything like that. We're just going to find the derivative as we see it. So, the derivative of 9x squared. That's easy, right? You should just get 18x equals, now to find the derivative of 5y to the 7th. Notice this chain rule. You have the function y within the function of to the power of 7. So, my answer then is going to be 5 times, because remember you just, whatever constant's out front, you just keep it there. I bring down my exponent, and it becomes y to the 6th. So that's derivative of the outer function. And now I've got to multiply that by the derivative of the inner function, which is just y here. So the derivative of y is y prime.
Why don't you just put 35?
Now, if you did this and you went straight to writing it as 35 y to the 6 y prime, that's fine. But just trying to make it super clear about what goes where and why. But then we do have one more step. The last step here, solve this equation for y prime. And so, this is what we end up with for y prime. Does this reduce? Does that simplify at all? Nope. It doesn't simplify at all. So then, that means we're done. That's your final answer. There's your implicit derivative. Notice in this case, if we were trying to find the slope of the tangent line at a point, notice in this case, I would actually have to plug in the x-coordinate and the y-coordinate, both, in order to figure out what the derivative was. Remember some of those crazy graphs you saw yesterday? They weren't functions. There were multiple points oftentimes for a single x value. And so that's why it takes both of these on implicit functions, or implicit equations, because they often aren't functions. You've now seen a couple polynomial-based ones. Now I want to see, can you apply it to something that looks like this, with a sign in there? So, take a moment, write it down, and go ahead and find the derivative, and then we'll take a look at here together in a moment after you've had a chance to think it through. So, to find our derivative here, I'm going to start by doing the derivative of sine of y. Now notice it's sine of y, not sine of x. So we have a chain rule situation. The function y is inside of sine. So derivative of the outer function, that's the derivative of sine. That's going to give me cosine of the same thing. So it's going to be cosine of y times derivative of the inner function. Remember the inner function is y here, so derivative of y is y prime. Equals. Now we do the derivative of pi x. Now pi is just a constant, of course. So it might as well be 5x or 7x or something like that. The derivative is just going to be pi. Now, having gotten this far, we still have one more step. We still have to solve it for y prime. So that means we divide both sides in this case by cosine of y. Y prime will equal pi over cosine of y. So to find this derivative, notice it doesn't say implicitly. It just says find the derivative. Yeah. That's because it's just assumed that with it being written implicitly that we have to find the derivative implicitly as well. All right, so to find our derivative, I start by doing the derivative of x, which of course is just 1.
Okay.
Plus the derivative of y,
1.
which is y prime.
Yo, I don't like this at all.
All right, now, the left side was pretty easy, although, I mean, sometimes we get tripped up on those, which is why I put them in there like that, because we might look at the y and think the derivative is 1 out of reflex, because we're so used to seeing that with the x. We're kind of retraining our brain a little bit here. But on the right side, this is x times y. That means product rule.
Oh,
And so, for product rule, I'm going to do original times derivative. So I'm going to do x times the derivative of y. Remember, the derivative of y, of course, is y prime. Plus derivative times original. The derivative of x is 1 times y is just going to be y.
Yo, dog.
So there's our implicit derivative. Although we're not going to be done yet. We're still going to have to solve for y prime. But make sure you got this part first. All right, so from here, we got to solve this for y prime, which is its own little puzzle of algebra to do, right? Step 1, move all the y prime terms to one side, and move all the non-y prime terms to the other side. It doesn't matter which way you go technically with this. I'm just going to move the y primes. I'm going to choose to move the y primes on the left side. So I moved my y prime terms to the left side, so that meant subtracting the xy prime from both sides. And I moved everything that didn't have y prime to the right side, so that meant subtracting 1 from both sides. Now that I've gotten here, do you see how we can get the y prime by itself? The interesting thing is this is actually a point where a lot of people have trouble. The trick is in factoring. Because you'll notice that on the left-hand side, I can factor y prime out of both terms. Now, once you've factored out that y prime, now you can actually get y prime equals. So you got one last step.
Oh, you do?
Solve it for y prime now. All right. This then is your final answer. We ended up getting the whole thing down to y prime equals. We're done. Nothing else to do here.